Look at this steaming cup of tea. It has two spoons resting inside, one made of shiny metal and one made of wood. If you grab the metal spoon, it burns your fingers, but the wooden spoon is perfectly cool. The liquid they are sitting in is exactly the same temperature, so why do they feel so different to the touch? For centuries, the leading theory was that heat was an invisible fluid called caloric that physically poured from hot objects into cold ones. We now know that heat is kinetic energy. It is the physical motion of atoms and molecules constantly trying to balance themselves out by moving from areas of high energy to areas of low energy. To see how this works, look at this animated diagram of the metal spoon. Its atoms are arranged in a grid of closely packed spheres. When the bottom spheres sit in the hot tea, they absorb that thermal energy and vibrate violently. Because they are packed so tightly, they immediately strike the atoms above them, passing that kinetic energy upward. This specific chain reaction is called conduction. It relies entirely on direct physical contact. One particle hits the next, transferring energy millimeter by millimeter up the handle until it reaches your hand. The wooden spoon is different. It has a highly disorganized, spaced-out atomic structure. When the atoms at the bottom of the wood vibrate, they have a much harder time colliding with their neighbors. The kinetic wave simply fizzles out, making wood a very poor conductor. Effective insulation depends on these structural gaps. Rather than relying on simple thickness, these materials use trapped air to prevent microscopic collisions from chaining together. Survival in the Antarctic depends on managing this physical contact. As these emperor penguins huddle, their specialized feathers trap a layer of disorganized, non-conducting air right against their skin. This buffer stops particle-to-particle collisions with the freezing wind before they can reach the body. That explains solid objects, but what about the air in a room or the water in the ocean? They don't have a rigid, fixed structure of particles to pass vibrations along. So how does heat travel through them? This cross-section shows a heat source at the bottom of a container filled with fluid. When the loosely packed particles in a liquid or gas heat up, they gain energy and spread out. This expansion makes the heated fluid less dense than the cooler fluid around it, causing it to float upward. As that hot fluid rises, the cooler, denser fluid is forced to sink down the sides to replace it. Once it reaches the bottom, it heats up, expands, and rises too, creating a continuous circular flow. This process is called convection. Unlike conduction, where particles stay mostly in place and just bump into each other, convection requires the actual physical transportation of the fluid mass itself from one place to another. If you scale this dynamic up, you get a regional weather system. During the day, solid land heats up much faster than the ocean. The air above the land expands and rises, creating a massive thermal updraft. To fill that empty space, cooler, denser air from over the ocean is pulled inland. These invisible circular fluid loops are the exact mechanisms we feel as coastal land sea breezes. They are the underlying engines driving regional weather patterns across the globe. How does the sun's heat reach Earth through the absolute vacuum of space, where there are no particles to touch and no fluids to move? The answer is a third pathway. Looking at this blinding sunburst over the Earth's horizon, you are seeing thermal radiation. It is an electromagnetic wave that requires absolutely no physical medium to cross those millions of miles of empty space. All hot bodies emit these radiant waves. Touching a hot stove burns you instantly through conduction, but you can feel the warmth of a fire on your face from 10 feet away, or feel the sun's heat from 150 million kilometers away. What happens to those radiant waves when they finally hit an object depends entirely on a property called emissivity. Emissivity is a measure of how efficiently a surface emits or absorbs thermal energy, dictated largely by its color and texture. You can see this clearly in this split-screen diagram. On the left, a dark, rough surface absorbs the incoming waves and quickly heats up, glowing red. On the right, a light, smooth surface reflects those exact same waves away, remaining completely cool. Radiation allows energy to bypass matter entirely. It is how solar heat warms our planet across 150 million kilometers of nothingness, driving every biological and geological process on the surface. Nowhere do these three pathways overlap more perfectly than in the Earth's water cycle. It is an enormous system for sustaining life, driven entirely by the movement of heat. Look at this landscape cross-section. The cycle begins with radiation. Yellow waves of thermal energy from the sun travel through space and strike the ocean surface. This provides the energy required for liquid water to evaporate and rise as vapor. Once in the air, massive convection currents take over. They carry this warm, moist air high into the atmosphere. As the air rises, it loses heat, condenses into clouds, and eventually falls back to the surface as rain. But the cycle continues underground through a process called infiltration. Infiltration occurs when that precipitated water seeps downward through the porous gaps in gravel and sand. As we pan below the surface level here, you can see that water seeping through the distinct brown soil layers until it collects in a deep blue underground reservoir. These deep layers of sediment and rock that store our slowly moving groundwater are called aquifers. While nature runs on these massive thermal cycles, modern human civilization is built entirely on our ability to manipulate these exact same pathways. Look at this simple blue thermos flask. It keeps your coffee hot because it is engineered to block all three pathways simultaneously. A vacuum layer stops conduction and convection, while a reflective inner coating bounces thermal radiation back into the liquid. And look at the woman adjusting the vents on this vintage window air conditioner. Early modern appliances manipulated fluid convection and forced chemical refrigerants to change states, all to control our indoor climates against the outdoor elements. From the coastal weatherfront to the spoon in a teacup, the same three pathways govern how energy moves. Understanding these invisible mechanics explains why the water cycle flows, how our technology functions, and how life maintains its balance against the environment.